All right. Good morning, my lovely kiddos and my future mathematicians. Today we are talking about 9.4a. We're completely skipping over 9.3. And today we're going to be talking about tangent ratios. Now, tangent ratios and two others that we will be talking about in the future here are examples of trigonometric ratios or trig ratios. Now, a trigonometric ratio is a ratio of lengths of two sides of a right triangle. All right, so these work with right triangles. All right, so specifically today we are talking about tangent ratios. And the tangent ratio is the ratio, so remember those look like fractions, of the opposite side to the adjacent side. All right, so our ratio or that fraction is going to look like the opposite over the adjacent. So we're going to have the tangent of some angle, which we don't know, is equal to the opposite over adjacent. An easy little saying, phrase thing that we can memorize this and the other trig ratios are TOA. Okay, so this is the one for tangent. It stands for tangent is opposite over adjacent. All right, so let's go ahead and do an example with no numbers here, just the concept. So we're going to have our right triangle. And we're going to have the points C, B, and A. As I said, it is a right triangle. All right, so we are only dealing with our opposite and adjacent sides. We are not dealing with our hypotenuse at all today. So we are only talking about angle C and angle A. We're not going to be talking about angle B at all because its opposite side is the hypotenuse, and we're not going to use that today. All right, so we can do the tangent of A, that angle, and the tangent of C. All right, so looking at angle A here, we want to do its opposite sides, the side that it's farthest from the side that it is not touching. Okay, so we can see that angle A touches this side on the bottom, BA, and it touches our hypotenuse, CA. So the side that angle A is not touching, its opposite side, the side furthest from angle A, is this one right here, side BC. Okay? Over its adjacent side. Again, we're looking at the legs, we're not looking at the hypotenuse. So the side that is adjacent next to or touching angle A is going to be this bottom side, BA. All right? Now switching over to angle C here, again, we're looking at its opposite side. The side furthest from the side not touching angle C is going to be down here. That is going to be the side BA. And then its adjacent side that is not the hypotenuse, the side that is touching angle C is going to be this side here, BA. All right, and if we pay BC. I wrote that wrong, BC. All right, and if we take a peek here, we can realize that tangent of A, BC over BA, is the reciprocal or the flipped fraction of our tangent of C, BA over BC. All right, so that could come in handy for a little shortcut in a minute here, okay? Now let's do an example with numbers and everything so we can go ahead and get some practice in. So our first example here today, we have our right triangle, very important. We need a right triangle to do our trig ratios. We have points X, Z, and Y. we have the side lengths of 20, 25, and 15. Okay, so again, we can only use the tangent of A and the tangent of Z. We can't use the tangent of Y because its opposite side is the hypotenuse, and we're not dealing with the hypotenuse today. So the tangent of X, okay? So we want to look opposite over adjacent again. So from angle X, the opposite side, the side furthest from, the side not touching angle X, is going to be this side here, YZ, that is 15 units long. And then the adjacent side, the leg that is touching, that is not the hypotenuse, angle X is going to be this side here, YX, at 20 units. Now we're going to use our knowledge from way back in 8.1a, where we want to reduce our ratios by its greatest common factor, in this case 5. 15 divided by 5 gives us 3, and 20 divided by 5 gives us 4. So the tangent of x is 3/4. All right, now looking at the tangent of z, again, we want to pick its opposite side, the side not touching. The side furthest from angle Z is going to be this side over here, YX, at 20 units long. And then the leg adjacent to angle Z, the side that is touching angle Z that is not the hypotenuse, is YZ at 15 units. Again, we're going to reduce by its greatest common factor of 5 again. 20 divided by 5 is 4, and 15 divided by 5 is 3. And we can once again see that the tangent of one of the angles is the reciprocal of the other. 3/4 and 4/3, they are reciprocals. They are flipped fractions, okay? So we could use that shortcut by only finding the tangent of one of the angles and then flipping the fraction for the other one. All right, so let's do that on this example here. So here in our second example, we once again have our right triangle. Here we have points A, B, and C. Okay, where CB is 14, AB is 48, and AC is 50. Again, we can only find the tangent ratios of A and C because B, the opposite side from B, is our hypotenuse, and we're not going to use our hypotenuse with the tangent ratios. So the tangent of A, we want to take the angle, the side furthest from, the angle opposite, the side not touching angle A, which is going to be this side CB at 14 units long. And then the leg adjacent, the leg touching, the side that is not the hypotenuse here, for angle A, which is the side AB at 48 units. Okay, we are going to divide by its greatest common factor of 2 this time. 14 divided by 2 is 7, and 48 divided by 2 is 24. Now that is as reduced as it can get. 7 does not go into 24, and we cannot pull anything else out. Okay, and then instead of doing all the same work for the tangent of C, which would be 48 over 14, having to reduce that same by the same greatest common factor, we could recognize that we have those reciprocals and that the tangent of C is just going to be the reciprocal of the tangent of A, 24 over 7. All right, now we have fractions here, but it is important to realize that these do have decimal approximations as well. If we were to take 24 divided by 7, we would get a decimal approximation, 3.42857, blah, 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 blah. All right, so even though we're used to seeing these now as fractions, they can come out as decimal approximations. All right, so that's going to be the next new thing that we learn. How do we see our decimal approximations? All right, so when we are given the tangent of some number, so if I tell you the tangent of some number, all right, then it is going to give you some kind of decimal here. All right, and we're going to get that by plugging it into the calculator. So our first example here is just the tangent of 35 degrees. All right, so we're going to take our calculators again. We're going to hit this button right here that says tangent. So we hit our function tangent, and then we type in the number of degrees, which was 35, and simply hit enter. Now, just as per usual, I only want 3 numbers after the decimal, so this one will be 0.700. So we're going to write that down, 0.700. All right, the second one is going to be the tangent of 45 degrees. So again, taking our calculators, hitting that tangent function, typing in our number of degrees, closing our parentheses, and hitting enter, we can see that the tangent of 45 is just 1. Okay, so no decimals to transfer down here, just 1. And then our third and final example for today is going to be the tangent of 100 degrees. So we are going to touch our button tangent, type in our degrees, which was 100, close our parentheses, and hit enter to see that the tangent of 100, that ratio in decimal form, is negative 5.671. Again, only 3 numbers after the decimal point. So we have negative 5.671.